Hello class. In lesson 4.4, solving right triangles, you'll learn to use trigonometric functions to solve right triangles and use angle of elevation / depression to solve real world applications. Now, we know from the previous lesson that the sine, cosine, and tangent on a right triangle is equivalent to the following ratio. Sine is the opposite over the hypotenuse. Cosine is the adjacent side divided by the hypotenuse, and tangent is the opposites divided by the adjacents. Now, a very easy mnemonic device to memorize that is again the term SOHCAHTOA, where in SO the S stands for sine, the O and the H stands for opposite over hypotenuse, and then C stands for cosine, A is for the adjacent, and H is going to be for the hypotenuse. And TOA, finally, T for tangent, O for opposite, and A for adjacent. So you can use this mnemonic device again to know what the ratios of each trig function equals. Now, how do we use this? Well, we use this for one application is to find the missing side on a right triangle. So let's say we're looking for this side right here, given this angle and this side. Well, using these two sides, we're looking for this side, and given this side, which as we can clearly see is across the 90-degree angle, that is our hypotenuse. Now, since the opposite side of the angle that we're using is going to be this side over here, this side is the adjacent side. So without doing any extra work, we can identify the trig function that we use here by using the adjacent side and the hypotenuse, which again, using our acronym SOHCAHTOA, is going to be the middle one. Since we're looking for the adjacent side and we are given the hypotenuse, we're going to use the cosine. So setting up my equation as the cosine of 48 degrees equals to the adjacent side of x divided by the hypotenuse of 8.2, we're going to solve this equation by simply cross multiplying. So x equals 8.2 times the cosine of 48 degrees. And let's see what that equals to. So let me clear all this. So 8.2 times the cosine of 48 degrees. Oh, let me just double check real quick. Yeah, my calculator is set at degrees. All right. Yes, that is the answer. So my answer here our answer here is that x equals to 5 point, oh, I forgot the number already. 5.5. So there's your answer. Let's look at another example. So for this example right here, we are given again this angle down here and labeling again 6 because it's on the opposite of this angle is going to be the opposite side of that angle. And again, since x, the side that we're looking for now, is on the opposite side of the 90-degree angle, this is your hypotenuse. So from the term SOHCAHTOA, given that we're looking for the hypotenuse, okay, that's going to use either cosine or sine or cosine. And given that we're looking for the hypotenuse and that we are actually given the opposite side, that means we're going to use the first one, sine. So to use the opposite side to find the hypotenuse, that was going to use sine of our angle. So sine of 43 equals to the opposite side of 6 divided by the hypotenuse x. And we're going to solve this again by cross multiplying. But here is a problem. Since cross multiplying is going to multiply the sine of 43 by x, well, what we're going to end up doing, because we're going to cross multiply, we're going to end up with x times the sine of 43 equals 6. So to solve for x here, we're going to have to divide by the sine of 43, so this can reduce to 1. And of course, what I do to one side of the equation, I have to do to the other side. So here, x equals to 6 divided by the sine of 43 degrees. And if you notice, instead of multiplying 6 by this, we end up dividing 6 by this value. And you're going to see that this is going to happen every single time when I set up my equation and my variable x is in my denominator, and the x is what's going to be cross multiplied. Ultimately, I'm going to end up with this numerator divided by my trig function, the angle of my trig function. So here, let's see what the value is. So 6 divided by the sine of 43 degrees, that is approximately 8.8. So there's your answer. Let's do another example. Now in this example here, again, notice our angle is up here, and opposite of that angle is the opposite side. And next to that angle is the adjacent side. Here, our hypotenuse is this side right here, but that's useless because we're not looking for the hypotenuse, because obviously the x is here, nor are we given any information about the hypotenuse, how long that is. So the hypotenuse is not going to be useful. So from our acronym of SOHCAHTOA, given that we know that, given that we're looking for x and that the opposite is 3.8, we know the opposite and we're looking for the adjacent side. So that means we're going to use the last one. So the equation we're going to set up is the tangent of this angle of 46 equals to the opposite side of 3.8 divided by the adjacent side, which again is x. And as you can clearly see from just like the last example, when I cross multiply here in order to solve this equation, I end up starting by multiplying x with this. So what's going to end up happening is the same thing as before. So x, as the previous example, so x can be simply set up by getting 3.8 and dividing it by the tangent and not times the tangent. So this is going to happen again every single time, like I mentioned. Whenever our denominator is a variable, we end up dividing these two quantities instead of multiplying the number to the side with the trig of the angle, with the trig function of the angle. So let's now type that in. So 3.8 divided by the tangent of our angle, that gives us approximately 3.7. So there's your approximated answer. Here's the exact answer and your approximated answer to the 1 decimal point. Now, to find the missing angles, since the sine of theta equals to the opposite over the hypotenuse, the way that we find the angle theta is that we take what's called the arc sine, the inverse of sine, which is denoted as this notation here. Sine to the negative 1 power. By doing that operation to the left side of the equation and the right side of our equation, okay, that's what this one's called. That's called the arc sine. By doing that to both sides of the equation, this is the inverse to sine. So the sine and the arc sine are going to cancel each other out, and we end up that theta is simply going to equal to the arc sine, or the sine inverse, of the opposite divided by the hypotenuse. So doing this operation every single time, and given that we set up an equation like this, we can figure out theta, the angle, by doing this operation to both sides, this arc sine to both sides. And well, the same thing is going to be true with every single one of them. The inverse of cosine is arc cosine, which is denoted as cosine with a negative 1. So here, since the cosine of theta equals the adjacent over the hypotenuse, that means theta will equal to the arc cosine of the adjacent over the hypotenuse. And the same thing is true about tangent. Since the tangent of theta is the opposite over the adjacent, the arctangent of the opposite over the adjacent side will equal to the angle of theta. Okay, so this is referred to as the arc cosine, and this is the arc tangent. Arc cosine. So let's use again this technique to find the missing angles on a triangle. Now again, we have to first decide and determine which of the three trig functions I need to use, sine, cosine, or tangent. And that's going to again depend on the sides that I'm given on the triangle. Since I'm looking for this angle here, theta, and 14.7 is on the opposite side, this is the opposite of that angle. And since this angle that's next to it, 8, is the adjacent side, not the hypotenuse. Here's the hypotenuse, because that's always across the 90-degree angle. This is the adjacent side. Then the trig function I'm going to use is tangent, since the tangent of theta equals the opposite over the adjacent. So plugging in my values, I get that the tangent of theta is the opposite side of 14.7 divided by 8. And since I'm looking for theta, well, remember, all I have to do from here is simply take the arc sine of both sides. So I would get that theta, because the arctangent, not sine, the arctangent and tangent are going to cancel each other out, so I'm left with theta, and taking the arctangent of this side gives me the arctan of 14.7 divided by 8. So now let's use our calculator. On our 84, the arctangent, arcsine, and arccosine are above their respective trig functions. I just simply have to hit the second key and then tangent, and I get the arctan. Now inside my parentheses, I type in 14.7, divide that by 8, and my approximated value for the angle theta is 61.4 degrees. Let's see, let's do another example. So here, let's see which trig function do we use. Well, again, given that our angle is down here, this side is the opposite side of our angle, and this side is not the adjacent side. Okay, the adjacent side is next to our angle, but is not across the 90-degree angle. So in this situation, because the 7 is across the 90-degree angle, that's the hypotenuse and not the adjacent side. The adjacent side will be the other side. Remember that the opposite side, here let me highlight the opposite side. The opposite side and the adjacent side to our angle always intersect at a 90-degree angle, okay? So that's another way to determine which one's the adjacent side. The hypotenuse is always the side opposite of the 90-degree angle. So here, 7 is a hypotenuse. Well, the trig function that uses the opposite and the hypotenuse, that's sine. The sine of theta equals the opposite over the hypotenuse. So setting up our equation, we get that the sine of theta is 3.2 divided by 7. And therefore, theta will equal the arc sine of 3.2 over 7. Let's enter that in our calculator. So 3.2 divided by 7, that's going to give us an approximated value of 27.2. And there's your angle theta. One more example. So let's see it here. So this side over here is the hypotenuse, since we can clearly see that's across the 90-degree angle. And now it's just determining that side right there. Well, obviously it is not the opposite side, since the angle is here. This side would be the opposite. So we can see again, notice again, that this side is next to the angle. So that's your adjacent side, not your hypotenuse, okay? This is not the hypotenuse. Remember, the hypotenuse is always across that angle right there. So the two sides that are always next to your angle theta are your adjacent and your hypotenuse. So the one that's opposite is obviously your opposite. Now, the trig function that uses the adjacent and the hypotenuse is cosine. So cosine of theta equals to the division of the adjacent side by the hypotenuse, by that ratio. So plugging in the number 12 for the adjacent and 15 for the hypotenuse. Now I notice again that this is reducible. You don't have to reduce this fraction. If you want to reduce the fraction because it does have a common factor of 3, you can, but you don't have to, since we're going to take the cosine of that. And that number again, whether it's 12 over 15 or 4 over 5, is still the same number. It's just in a reduced form, and that's not going to matter when we take the arc cosine. So theta equals the arc cosine of 12 over 15 of 12 over 15, which is approximately 36.9. And like I said, you don't have to reduce your fraction. Notice that if I did reduce this by the common factor of 3, we would end up with 4 over 5. And notice that I get the exact same answer. And the reason for that, because again, they're the same number. This number and 3 and 4 over 5 are the same number. And since we're taking the cosine of the same number, we still end up with the exact same degree. So this is your solution. Now, the most common applications of using this, using right triangles, is for angles of elevation and angle of depression. Let's say again that in real world application, we have this angle of elevation and angle of depression. So because of this, we can create any triangle that I want. Like I could connect this and create a triangle. But for today's example, since we want to use this on right triangles, I'm going to end up drawing a vertical line and drawing a right triangle right here. And this angle theta that we see here, let me draw it in red, creates this right triangle. If I draw straight down a vertical line, where this would be the opposite side, the horizontal axis would be your adjacent side, and your hypotenuse would be the direct distance between your observer and your object. This is your direct distance. Now, height, again, anything that refers to your height, okay, or obviously vertical distance, is going to be, again, your opposite side. Anything that refers to as a horizontal distance or a base distance, the distance between bases, like the base of the building and the base of a ladder or a tree, anything like that, that's going to represent your adjacent side on your triangle. And then the same thing is true for your angle of depression. The only difference is that the angle, the horizontal part, is on top and it's going downwards. But again, if I draw a vertical line to the horizontal axis from my object, then I create again another right triangle where this is my opposite. The horizontal axis is the adjacent side. And again, the direct distance between your observer and the object is your hypotenuse. So you can just simply stick with these two default triangles and then use again your trigonometric functions to figuring out the missing side on that right triangle. So for example, let's look at an application of this. Let's say that we have a surveyor that is standing 115 feet from the base of the monument of a monument. That's weird. Okay. Now the surveyor, measures that the angle of elevation to the top of the mountain is 78.3. How tall is the monument? So since here we're told that we have an angle of elevation, we are going to use again this default right triangle, okay, where our angle theta is going to be right here, and that number is going to be 78.3. Now let's fill in the rest of the triangle. It says here that the surveyor is standing 115 feet from the base, again, base of the monument. So that means, again, this horizontal distance. So your horizontal distance is also referred to as the distance between two bases. So that's going to be 115. And we're asked to figure out the height of the monument, which is going to be a vertical distance. So that's going to be our x. So here we're going to use the trig function tangent of theta to find the opposite over the adjacent, because those are the two sides that are given to us. We're given, again, our adjacent side, and we're looking for the opposite. So that uses tangent. So plugging in the corresponding numbers and variable, we get this equation. And to solve this equation simply requires us to cross multiply. So x equals to 115 times the tangent of 78.3 degrees which is approximately 555.3 feet. Let me check the units. Yes, feet. So this is your approximated height of this monument that the surveyor is standing and looking at. Okay, let's look at another example. So again, let me read it first. We have a person here standing 85 meters from the base of a tower. If the tower is 200 meters tall, find the angle of elevation. So here we want to now find the angle of elevation from the ground where the person is standing to the top of the building. So let's draw this, again, default triangle. And our angle theta is going to be right there for every angle of elevation. We're going to draw the same triangle, and theta will be down there. So if the tower is 200 meters tall, so that's a vertical distance, so this is going to be 200. And the person, so tall means height, so that's a vertical distance. And if a person is 85 meters from the base, again, base is the horizontal distance, that's going to be 85. We're going to use tangent again because we're given the opposite and the adjacent side. So the tangent of theta is 200 over 85. And to solve this equation, we simply take the arctangent. We do not cross multiply. We take the arctangent because we're looking for the angle. So the arctangent of 200 over 85, that is approximately 66.97. So that estimates to 67 degrees. So that is your angle of elevation. So the person would have to turn up his head 67 degrees to see the top of the tower. Approximately, of course. Now, let's look at applications for the angle of depression. So let's say that the angle of depression from a helicopter to a landing pad is 34.9 degrees. If the horizontal distance from the helipad to the landing pad is 1,200 feet, find the altitude. Altitude is just another way of saying height to the of the helicopter. So since it's an angle of depression, the triangle that we draw for these type of problems is this part, okay, is this triangle right here, where our angle is going to be located there. Now, we can technically draw this triangle, an angle of elevation, and just put the angle right there and just do the same thing. Horizontal, vertical, and we end up with the same answer where our sides are in the same location. Our vertical distance, our horizontal distance will be in the same location, and this would be the opposite, just like this. This side is the adjacent, just like this, and those numbers will match up. But let's stick again to, since it's an angle of depression, let's get you comfortable again just understanding that we're looking at this because we're looking at this type of triangle because we're looking technically downwards. Okay, but you can get away with using the same triangle as the first two examples. However, let's stick, like I said, to this. So here our angle of depression is 34.9, so theta is 34.9. The horizontal distance the horizontal distance is 1200 feet. So that's going to be this value right there. Again, horizontal distance. And they're asking us to figure out the height, which is always a vertical distance in these situations. So this is going to be our x. So again, yet again, we use tangent because we're given the opposite side and the adjacent side. So we're going to use the tangent of theta as the opposite over the adjacent. The opposite side is x, the adjacent side is 1200. So here we end up cross multiplying. So x equals 1200 times the tangent of 34.9. Tangent of 34.9, and that approximates that the helicopter is 837.1 feet in the air. So this is your approximated answer. And for the last example, now let's find the angle of depression. So an example where we find the angle of depression. So again, by default, start by drawing this triangle here. Even though we're looking for the angle of depression, again, we're going to start with that angle there, and our angle theta will be here. This time, we don't know what our angle theta is. And let's read everything else. We have here that Samantha is sitting in a tree 32 feet from the base, feet above the ground watching a deer. Now, if the deer is 57 feet from the base of the tree, let's find this angle of depression from Sam to the deer. So we want to, again, figure out this angle there from up here looking down. Now, she is sitting, again, 32 feet above the ground. So that's going to be obviously a vertical distance. So this 32 feet on our triangle represents this vertical distance. And since the deer is 57 feet from the base of the tree, so again, we're assuming she's here, which she's on a tree, all right? This distance is the same as this distance right there. Again, that horizontal distance. Again, from base, that is going to be a horizontal distance, which is this value here, and that's 57. And because we're given the opposite and the adjacent side, we're going to, again, use tangent of theta to figure out our angle. So writing in the corresponding numbers, our equation is that the tangent of theta equals 32 over 57. And therefore, by taking the arctangent of both sides, theta equals the arctangent of 32 over 57. And that approximates to 29.3. And there is your approximated angle of depression. Well, that concludes the last example on solving right triangles using trigonometry. If you have any questions, please send me a message on Remind or through email. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.